Morning, everyone. I hope you guys are having a good start to your day. It is the 20th of November, and we have just a handful of classes left. Um, I'm going to go ahead and get rocking and rolling on things. So in order to do that, I've got to go to my presentation mode, start the presentation, then I got to share my screen, because otherwise then I'm just talking and you're looking at my face. Well, there's nothing that is displaying for you. Um, we are talking about and wrapping up our discussion of enzymes and enzyme mechanisms. Well, Monday's lecture. The recording or the PowerPoint? Sorry, Milo. Oh, must be the record. Oh, really? I'm so sorry. I thought that I did that. I will do that. That will be done today. I'm putting it on my list. Upload lectures. I'm sorry about that, Milo. And then today's, you won't have to wait, 2 days for that. I will get that as well. And Wednesdays. I'm sorry about that. Okay, so what we're talking about today is really getting into enzyme regulation. We're kind of wrapping that up. This is our kind of last element of enzymes. And then what I'm very excited about, and I hope that you guys are as well, is talking about lipids. And I like to talk about lipids because there's kind of a connection between, you know, like nutrition and diet. And I don't mean like diet, we're going to talk about diets. Um, but I feel like when it comes to a discussion of lipids, you kind of have to, you see a connection between, maybe health advice or dietary advice that you've heard over the years, and oh, we'll avoid this and take this, and or not take this, but get more of these and less of these. Because we're going to talk about lipids and we're going to talk about their metabolism. Now, with that said, enzyme regulation. So we talked about isozymes. Glucokinase and hexokinase are both examples of isozymes. They catalyze effectively the exact same reaction, but the difference is that they're in different locations. So they're in different locations, and therefore they get different substrates, and therefore they kind of serve different roles. Like glucokinase, for example, in the liver, well, what is one of the major functions that your liver is going to be doing for your body is it's going to be communicating to the rest of your body how much blood sugar, and it's going to be regulating your blood sugar level. So you wouldn't really want glucokinase, and I'm saying want as like a preference, but you wouldn't want glucokinase to be like, oh yeah, I can consume any and every sugar, because effectively that would be communicating, hey, good news, everyone. There's this much sugar. Well, you're not so much interested in how much sugar there is as you are about how much glucose there is in the bloodstream. We also talked about allosteric enzymes. In your allosteric enzymes, these are just like, this is the same thing effectively as an allosteric protein like hemoglobin. So a catalytic or an activity curve, a Michaelis-Menten, let me rephrase that, a Michaelis-Menten plot for this is going to look like such. Substrate, and it's going to have this sort of same curve as that of an oxygen binding curve for hemoglobin, because it's an allosterically regulated protein. So this protein will undergo a conformational change whenever it binds either its natural substrate or an activator of sorts, and then it will continue to kind of exhibit those changes. So there are enzymes that are allosterically regulated, and typically a negative feedback loop is a good example of allosteric regulation, which is what we see here, where isoleucine is kind of the final product in a metabolic pathway, and it kind of regulates upstream steps or upstream components of this. So then that brings us to, okay, covalent modification. All right, so covalent modification of enzymes and proteins is, well, basically I think that we've talked about this previously, but I want to bring it back, this idea of what's known as a post-translational modification. The post-translational modification is a chemical modification, add the addition of a chemical group to an amino acid after that protein has been synthesized. So we've got I'm going to draw my my linear protein or my kind of linear protein. Okay, that's my chain of amino acids. And then let's say right here, and okay, so here's my linear, and then here's my 3D fold of this protein. Okay, there we go. And this is functional right here. So this enzyme carries out a particular function. Now, I'm just the only reason that I included this linear model was so that I could kind of show you what it looks like, and give you the idea that this is a protein that gets a modification. The modification would occur to the 3D structure of the protein, though. So the protein's been translated. So at the ribosome, it gets translated. And then if it goes through like the endoplasmic reticulum or something like that, it's going to be processed a little bit. And that's where some of these post-translational modifications may occur. Again, this is not a cell biology class. Maybe I haven't said that, but this is not a cell biology class. So I don't need you to be so consumed with, oh, well, does it go to the ER? Does it go here? Does it go there? Don't worry about that. So a post-translational modification or covalent modification, we've got a total of, I think, three or four of them that we're going to talk about. We've got adenylation. Okay. And so that would be where, let's see, we've got an enzyme, we've got ATP, which is adenine or sugar, and at least one phosphate, but in ATP, we've got three phosphate groups there. And then one of the byproducts of this reaction is PPI, also known as inorganic pyrophosphate. So what that means is that our phosphate group, effectively, in adenylation, AMP, that whole molecule, the nitrogenous base, the sugar, and one phosphate gets added to our protein. So it would be here, like AMP is added here. And then in terms of the 3D model, let's look at it right here. So AMP would be right there. Okay, so I've got, sorry for my drawings there, but let me ask you this. If we're adding that, or sorry, that's going to be added to an amino acid in this protein. Now, my question for you is, what is adenine? What have we seen previously? And think about DNA and the double helix. What is adenine really good at? Like, what do we kind of rely on adenine to do? I'll give you a hint. It starts with an H. Add it to the chat if you know where I'm going with this.
Well, I
Milo, perfect. Absolutely. Hydrogen bonding. So adenine is really great at hydrogen bonding. Okay. And adenine, if you remember, adenine's really good at making two hydrogen bonds. Now, I want you to think about this from two angles. One angle is the chemical modification. So we've added this whole thing right here onto a tyrosine residue, which if you remember what tyrosine looks like, we've got that ring. I always think about this as a tire. Oh, tyro. Okay, so it's a tire with a hydroxyl group. So there's our tyrosine ring. This guy right here is good at making one hydrogen bond. Okay. Now, whenever this modification has occurred, this whole thing that I've got my star by replaces this OH group. Okay, so that OH group that was on a fairly or a relatively non-polar residue now has, I'm not gonna draw the whole thing because I'm not that proficient of an artist. Um, I like using that word proficient. We got a phosphate group there. Okay, so that phosphate, it's got a charge. It's got a negative charge. And then add to that, we've got a sugar, and then add to that a nitrogenous base. And that nitrogenous base is good at making, well, hydrogen bonds. So, you know, surface level question. Have we changed the the types of interactions that that tyrosine residue can engage in? Absolutely. For one, we've gone from one hydrogen bond to two hydrogen bonds, but also with a, you know, with a sugar that has a bunch of hydroxyl groups, which are polar groups, and then a negatively charged phosphate ion. So we've pretty fundamentally changed chemically what that tyrosine residue looks like and what it can interact with. In addition to that, my first question is, or my follow-up question is this group that I have a big star by, is that larger atomically than an OH group? Which one is larger, the AMP or the hydroxide group? AMP without a doubt. So the space that is occupied is going to be pretty different. Now, that's one angle. I want you to think about it in terms of the chemical composition of that R group as well as the space that it occupies. Okay, so those are pretty distinct changes. And then my next way of thinking about it, and this is the way that I want you to think about every covalent modification. So I'm going to put these items down here. Chemical difference or chem difference. And then the second level or the second angle would be, well, overall effect. Overall, I'm going to say overall impact. And this overall impact, that would be more like a physiological change, a physiological or enzyme function. Now, what commonly happens is whenever a protein receives a covalent modification, the activity of that enzyme changes. And not to say that it goes to, pick a completely different substrate, but instead it is going to be activated or deactivated. Now, this is something that I want you to, kind of have an open mind about this and, try to think about it objectively. Objectively, what has changed? Well, the chemical makeup of that amino acid R group. That's one thing that has changed. And this is for all chemical or covalent modifications. The next thing is that, well, now that enzyme's activity might increase. I don't want you to associate exclusively, oh, adenylation means this enzyme is activated, or methylation means this. So I want you to think about it as the activity is going to be impacted, positive or negative, and the degree of that is going to vary. I want you to have an open mind with that. Then the other kind of non-negotiable is, well, how much does this change the functional group's chemical makeup? So with that, let's look at a couple of these other modifications. We've got adenylation where, and I'm going to go ahead and erase some of this. Adenylation where this whole thing, the phosphate included, is added to a tyrosine residue. Now, that's a pretty dramatic change. A covalent modification or a methylation, and sorry, let me go back. What amino acid is that adenylation added to? It's added to tyrosine. No other amino acids can be adenylated. So I want you to associate adenylation or the modification with a specific amino acid. So tyrosine gets adenylated. Okay. Next up, methylation. Well, you have a glutamic acid or a glutamate residue. Okay, so what's the makeup of that? That would be a negatively charged polar group. And to that methyl group, that negatively charged group, you get, or to that R group, to that negatively charged glutamic acid, you get a methyl group. Well, let's think about the polarity of a methyl group. It's pretty non-polar. So I want you to associate adenylation and tyrosine, methylation, and glutamate. Now, enzymes commonly undergo this to exhibit a new activity. And so, does anyone have any questions about adenylation or methylation?
So then I pulled some like this.
Okay. Now, these modifications are totally reversible. So what that means, I always kind of think about it as, or I always think about covalent modifications as kind of like a light switch. You add it, that's effectively like turning the light on, or you remove it, that turns the light off, or vice versa. You add it and the enzyme is inhibited, and then you remove it in order to activate that enzyme. This is a reversible modification. We've previously talked about an irreversible covalent modification. Does anyone remember the irreversible covalent modification? I'll give you a hint. OGen. That's my hint.
Oh,
Add it to
yeah.
the chat if you know what I'm talking about. Okay, perfect. Zymogens. Zymogens are irreversibly modified. So when that peptide bond gets cut, it's done. It can't be kind of stitched back together or anything like that. Okay, I'm going to clear all my drawings, and now I'm going to show you a couple of other covalent modifications. Now, the covalent modification, or not a couple of other, but one other. Maybe the covalent modification that it kind of gets the all the pomp and circumstance is phosphorylation. And that's in part because we talk about phosphorylation of sugars. So we talk about, adding a phosphate with a sugar kinase onto something like glucose to make glucose 6-phosphate. Now, phosphorylation, think about what a phosphate group looks like. Well, a phosphate group on an amino acid is going to look a little bit like this. You have O, P, O, O, negative, negative. And this would be our R group that we added to it. So I'll just put CH2 there. So, well, whenever you add a phosphate group to an amino acid, you're making it or you're giving it two negative charges. Now, the amino acids that are pretty exclusively your phosphorylated residues or phosphorylatable would be tyrosine, serine, threonine, and histidine. Now, these vary a little bit from organism to organism. Um, and there are some other instances, but they're pretty few and far between. These are the most commonly phosphorylated residues. And these are the ones that I want you to think about with respect to phosphorylation. Now, what that looks like is we have here would be a serine. This is effectively the R group for a serine, CH2OH. Now, this is a serine on an enzyme known as phosphorylase B. This is kind of an inactive enzyme, and this enzyme actually has a pair of serine residues. Now, an enzyme known as phosphorylase kinase, and these names get tricky, so I apologize and be patient. Please, I'll be patient with you if you can be patient with me. Phosphorylase A is the more active form or version of phosphorylase B. Okay. When the enzyme phosphorylase kinase transfers a phosphate group, a pair of phosphate groups onto the serine number 14, those are both phosphorylated residues. Phosphorylase A, actually, let me go ahead and there we go. Okay. So let me clean this up a little bit. We have phosphorylase B, which is an enzyme that gets phosphorylated in two locations on two serine residues. And if you were to look at phosphorylase B whenever it doesn't have any phosphates, that's your less active form of this enzyme. And this is a regulatory enzyme that's going to turn on, glycogen breakdown. So this enzyme, phosphorylase B, gets phosphorylated, and whenever it is phosphorylated, it is in its active form. When it's not phosphorylated, it's in its less active form. Okay. Now, what actually phosphorylates phosphorylase B is another enzyme. And that other enzyme, try to break this down a little bit. That other enzyme is an enzyme known as phosphorylase kinase. Okay, so phosphorylase A and B are your active or inactive forms. Phosphorylase kinase is responsible for either phosphorylating to make the active form or the enzyme that does the opposite action is known as phosphorylase phosphatase. So that term right there, phosphatase, I want you to think about that typically as removing of a phosphate group. And that phosphorylase phosphatase, what it's going to do is it's going to take our active form of our enzyme and make it the less active form. Alternatively, phosphorylase kinase will take our less active form to make our active form of our enzyme. Now, takeaways from this. First of all, I want you to think back to objectively what are the residues that are getting altered and how do they change? Tyrosine has a hydroxyl group or a hydroxide group. Serine has a hydroxide group. Threonine has a hydroxide group. Histidine lacks a hydroxide group, but it's got a bunch of nitrogens in that ring. So those nitrogens are kind of ripe for the addition of a phosphate. So objectively, I want you to think about these as all polar, or maybe tyrosine to a little bit less of a degree, but it's still a polar residue. I want you to think about those, your targets as, oh, well, it's a polar residue. And then whenever it gets a phosphate group, it's a polar negatively charged residue. So I want you to think about your residues that get phosphorylated as being polar uncharged. And then when they get phosphorylated, it is a polar charged or polar negative residue. Then this is, I think, a good example. What I want you to know about these is I want you to know the differences between phosphorylase phosphatase and phosphorylase kinase. So I might give you an explicit question. What does phosphorylase kinase do? What does phosphatase do? And then think about the ways that I could word that question. Well, phosphorylase phosphatase acts on phosphorylase A, or it acts on phosphor. Let me think for just a split second. Okay, what is phosphorylase phosphatase going to act on? The dephosphorylated substrate or the phosphorylated substrate. That way, I kind of remove the specific details and instead focus on, well, what's the word that I want you to take away from this is that phosphatase. And I want you to take away phosphatase and kinase because I want you to think kinase adds a phosphate, phosphatase removes phosphates. It could be multiple phosphates. Okay. Does anyone have any questions about these covalent modification or this covalent modification? And then I'll jump back. We've got adenylation, methylation, in phosphorylation. I want you to be comfortable with those covalent modifications, specifically the residues that they get added to. What is B phosphorylated by? That's a great question. So phosphorylase B, thank you very much for asking that, Darlene. Phosphorylase B is going to be phosphorylated by phosphorylase kinase. So I'm going to draw a little box to highlight the part that we're really interested in. This, think about this arrow right here. That is phosphorylase kinase is going to imagine that I'm phosphorylase kinase. With one hand, I'm going to grab phosphorylase B, my coffee mug. And then with my other hand, my other part of my substrate binding site, I'm going to bind this capsule of or this bottle of vitamin D supplements. And then that would be my two ATPs. So I am phosphorylase kinase. Here's my two ATPs, and here is my phosphorylase B. I will bring these together, and then I will release phosphorylase A, the active form of the enzyme, and then I'll also release two ADP molecules. Does that help?
Because when you answer it, you really don't have that much time, so you're not gonna go into.
Great, I'm happy to hear that. Okay, are there any other questions related to this? Because if there aren't, I've got a top hat question that we're going to tackle real quick.
So you would first say,
All right. Let me clear all my drawings. Done. And then let's go. Okay, so my top hat question, or our top hat question is, what is the term that's used to describe hexokinase and glucokinase? I think we've got 30 seconds for this question, so let's go ahead and go.
and then we go like it's like, you know, you don't really go into that much detail, but it's like more like but
Okay, 10 seconds left.
has a timer at the top. Did you see the timer at the top?
All right. I think that we're probably going to be at about 100% on this one. Pretty darn close. 91%. That's solid. Um, the three people who selected panzozymes, epimerazymes, and 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 allozymes, um, those are incorrect. Our correct name is isozyme because they're basically doing the same thing. Okay, I got a private message of, and this might be something that other folks are encountering. The Top Hat is updating. We're going to have another question, and whenever we do Top Hat questions, really what I'm looking for you is to answer at least one of the questions in order to get credit for that. So that's kind of my approach for Top Hat questions. So I'm just going to go ahead and proceed. So I don't want that to sound dismissive and like cold, but we're going to get to other Top Hat questions. But if your Top Hat needs to be updated, now's a good time to do that so that we get to it before our next question. And I know that you did not plan that. This wasn't like orchestrated. Okay, so now what we're going to talk about, I'm going to resume my share, lipids. I love lipids. I love the discussion of lipids because it's, to me, it's something where you talk about, it's almost like you bring a little bit of organic chemistry into biological function or into biology. And I think one of the reasons that they fascinate me is because most everything that we talk about is a is in an aqueous environment. And sure, we talk about, oh, well, there's the hydrophobic effect, and that influences protein folding. Yeah, that's absolutely true. But lipids are unique because they're such a huge part of every cell, of every living organism. And they have a part of them that is absolutely like super non-polar. And I don't think that's the best terminology, but that's something that always kind of it strikes me as interesting. Then in addition to that, you know, lipids make most things taste better, to be honest with you.
Oh, it does that?
Like, why is ice cream good? Because it's got lots of fat. It's got lots of sugar too, but it kind of balances out. Um, so that's one of the reasons that I like lipids. Now, lipids are substances of biological organism or origin that are soluble in organic solvents. Okay, so like hexane, a lipid would dissolve really well in hexane or decane or nonane or any number of other organic solvents. And yes, I know that there are other organic solvents, but I always like to just go to hydrocarbons. Now, lipids perform three major biological functions. One is that they form a bilayer. Okay, so a bilayer and are essential components of biological membranes. Now, whenever I hear that and whenever I read that sentence, what I want to stress to you is that your biological membrane is just one enormous bilayer. Okay. So that wording always kind of strikes me as like, well, what is it trying to say here? Well, a biological membrane or a membrane is going to be a bilayer and it's going to be largely contiguous throughout. Now, lipids containing hydrocarbon side chains serve as tremendous energy stores. And I always like to bring this up. There was uh, let me see if I remember his name. Um, there's a story that every few years it populates on Reddit and other internet pages. Um, and it's about a fellow, his last name is Barbieri. And I cannot remember his first name at the moment, but last name is Barbieri. And I think it was like I'm going to say 60s to 70s, somewhere within that range, he fasted for like 370 days. I know it was over a year. I don't know how many days. That says fasted, not farted. He fasted for 370 days. And I apologize for not saying flatulence. He fasted for 370 days. Okay, that sounds like
Yeah.
unreal. Yeah, absolutely. Well, he was, I think at the time that he began his fast, um, in terms of his body fat percentage, it was a very high percentage. He was, by all clinical definitions, he was considered morbidly obese. Morbidly obese. Um, and that word morbid meaning like his obesity level was borderline. It was in going in a direction that it was going to kill him. Now, when he fasted, he took vitamins. I hear you, Darlene. Um, so to answer, I don't know. I mean, that's like to me, that's like a discipline that is like, wow. I just can't imagine that. So the level of discipline that this guy had was just outrageous. If I remember his story correctly, which I'm sure I'm a little bit uh, off on the details, but he would, have very regular meetings with his team of physicians and dietitians. He took vitamins, multivitamins, and just to make sure that his body had the nutrients that were essential to carry out uh, energy producing processes. Um, and in that time, his like his weight just plummeted. And again, the details are a little bit murky. But if you do a Google search for Barbieri fast, I'm guessing that you're going to find this guy. I think that he was like, 550 pounds. And then over that 370-day fast, he dropped to like 180 pounds. It was it was an astronomical amount of weight loss. And I bring this up because how was he able to do that? I mean, discipline. Oh my gosh, this guy could, that's outrageous. That's crazy. But also, his body had so many fat stores, so much fat stored that he could extract energy from that. And I like to bring that up just because I know that, I have little kids and they have there are different things that like they recognize. Yes, absolutely, Hannah. Um, one of my kids will pick up like I don't have one in my office. I have vitamin D pills, but I don't have any sort of like a soda bottle or anything like that. But he'll pick up a soda bottle and he'll say, this has 180 calories. And then he'll pick something else up and he'll be like, this is 220 calories. And as a parent, that kind of makes me nervous because I don't want him to associate like and put like a shame or a guilt or a positive or a negative to calories. Um, because then that can lead to like eating disorders, and that's horrible. So I do my best to just be like, yes, it does, kind of be very objective and carry on the conversation, not stifle it. Um, but when it comes to lipids, they have tons and tons of calories. They have like a calorie is a unit of measurement. It's not a positive or a negative. And I think when it comes to lipids, well, if we thought about them and when we think about them as fuel sources and understand the like kind of thermodynamics of them, that's a great place to be in my opinion, in my thoughts. Um, I just, yeah, that's just my kind of aside as a parent. Okay, so lipids have a huge amount of energy. And so, are fats good or fatty acids good or bad? Well, they have a huge amount of energy. And so when you eat or when you ingest lots of fats, well, you're bringing in lots of energy. I think then not necessarily from like a shame perspective or a good or a bad thing, but it's if you think about it as a currency, well, then you can potentially do something with that. And of course, that is tremendously oversimplifying um, physiology and, you know, hormonal balance and how different bodies process different things. But on a very, very minimal surface level, lipids are huge energy stores. I want to talk about that. So, many intra and intra, so the other component of what lipids do is they are involved in lots of different signaling processes. So if you've ever heard of, or like vitamin D, for instance, that is a signaling molecule. Um, okay. Now, when it comes to lipid classification, one thing that I will recognize that, or that I recognize that I do make I'll call it a mistake, is I regularly use the terms lipids and fatty acids interchangeably. And that's not correct because a fatty acid is a lipid, but not all lipids are fatty acids. So I'll do my best to check myself on that. And that's largely because we start our conversation of lipids looking at fatty acids. Um, Lipids are also unique because of all our biological macromolecules, they don't polymerize. They are used, however, to make kind of larger molecules, and those larger molecules are triacylglycerols. Now, you can't really say that that's a polymer. I mean, it has a triacylglycerol has three fatty acids, but it's not a polymer in the same way that a tripeptide is a polymer, in the same way that a protein is a polymer. And likewise, if you think about a lipid bilayer or a biological membrane, well, most drawings for a membrane looks a little bit like this. So I recognize that that's something that I have to kind of improve on with my language and terminology. Glycerophospholipids, sphingolipids, and steroids are your last three lipids or your classifications for lipids. We're going to spend most of our time today and our continued discussion of lipids looking at fatty acids. And the reason that we look at fatty acids maybe the most is because of the fact that that's where lots of our terminology and our nomenclature comes from. When it comes to this last item here, intra and intercellular signaling events, most of those relate to glycerophospholipids, sphingolipids, and steroids. When it comes to energy stores, most of your energy stores relate to fatty acids and triacylglycerols. Okay. Now, and then, sorry, last but not least, I'm going to switch colors here and I'm going to use my highlighter function. A biological membrane. So the lipids that are involved in biological membranes, most of those are going to be your triacylglycerols and glycerophospholipids because it's those glycerophospholipids that give you and this is, I like to say this because I feel like many times people are like, they subconsciously say this with me. Um, the triacylglycerols and glycerophospholipids, but specifically the glycerophospholipids are the molecules that give your membranes that's right, polar head group and a non-polar tail. So that's one thing that whenever we talk about lipids, most often or when you talk about lipids in like a context of an organic chemistry class, you're usually talking about fatty acids, and then you'll also talk about glycerophospholipids. Now, I have a feeling that at least one of you guys in this class at this very moment has looked up Mr. Barbieri. I just have a confidence about that. Now, with that, let's go ahead and proceed. Okay. I appreciate that. That's fantastic. And it's kind of wild. A few years ago, I taught a nutrition or a biochemistry class for nutrition majors, and I remember like every single one of them, whenever I brought up this guy's story, they're like, "Oh, well, I'm guessing he gained the weight back." And I don't think that he actually did. I think that this is just like, okay, this won't be too much of a stretch, but I think that by not eating for an entire year, it pretty much fundamentally changed his relationship or association or his like I guess his how he looked at food. Okay. So fatty acids. I want to talk about this term, acids. Where's that term coming from? Why do we call them fatty acids? Well, they all have a carboxylic acid functional group. Now, as you can see here, this carboxylic acid in all of these is protonated. Now, in a physiological pH, well, that's actually not going to be protonated. But here we draw it where it's fully protonated. This double bond right here, since this is going to be a deprotonated group, that double bond is going to be, it's resonance stabilized, so that double bond isn't in one location. It's actually kind of in one of two locations at any given point in time. Now, with these fatty acids, we have a carboxylic acid with a long hydrocarbon chain side group. So this entire thing, this is I've always thought this is kind of crazy. Like this whole thing is considered a side chain or a side group. It's kind of funny because it's like, isn't that the whole thing? Yes and no. Okay, so here's our fatty acids, and they, looking at all three of these, all four of these, they have unique names. There's stearic acid, oleic acid, linoleic acid, and alpha linolenic acid. Now, every time I see alpha linolenic acid, I would say every two times I say it incorrectly because I have this habit of reading linoleic acid and then I say alpha linoleic acid. No, it's alpha linolenic acid. These are the names that are the common names for fatty acids. I don't expect you to know the names of the common names of fatty acids. Now, the predominant fatty acid chains in plants and animals is between 16 and 18 carbons long. Here, what we have are four examples of an 18 carbon long fatty acid. Now, the differences between these, in addition to their common names, they are either considered saturated or unsaturated. Now, the nomenclature that we use for that is pretty simple. So the C18 colon 0, the C indicates carbon, 18 is the number of carbons, and then this colon and the number that follows, which I'm going to go ahead and highlight that, indicates the number of double bonds or the degree of unsaturation. So I'm going to switch colors here. I'm going to go with red. I'm going to highlight, nope, that's not what I want to highlight. I want to highlight saturated. And then I'm going to highlight that right there. Okay, saturated is 18 colon 0. So this right here is a saturated fatty acid. It has nothing but single bonds. And you might look at that carboxylic acid and say, oh, but what about that double bond there? Well, I would argue with that that's not a double bond because it's resonance stabilized. Now, in addition to that, I would also say, well, they all have that same bond in question. But let's think about the side chain or that side group. When we talk about saturation versus unsaturation, that's what we're focused in on. Now, whenever we talk about unsaturated, we've got this right here, oleic acid, which is a monounsaturated fatty acid. We've got linoleic acid, which is our 18 colon 2 polyunsaturated fatty acid, and then 18 colon 3 or our alpha linoleic acid or I did it. Our alpha linolenic acid, which is our another polyunsaturated fatty acid. Okay. Now, this is one of the places that I always like to think about like diet advice or, general health advice. Typically, people are going to say, you shouldn't or you should have a diet that's richer in unsaturated and polyunsaturated fatty acids or PUFAs, polyunsaturated fatty acids, compared to saturated fatty acids. So if you were to eat a bunch of bacon, well, chances are you're going to be consuming lots of saturated fatty acids. Whereas if you eat some avocado, well, you're going to have more unsaturated fatty acids because most plants are going to produce more unsaturated fatty acids. Now, things like salmon. Salmon's rich in omega-3 fatty acids, which are an example of an unsaturated fatty acid, which we're going to get to that nomenclature in just a moment. Now, all of the double bonds in naturally occurring fatty acids have the cis configuration, which I know that this was a bigger thing whenever I was younger, but um, companies like McDonald's and most every fast food joint had to put notes up like or put a sign up that's like now made without trans fats. Okay, worth noting. And the significance of that is that cis fatty acids versus trans fatty acids are going to be metabolized in a different way. Now, what we'll get into in this class is we will talk about the metabolism of your cis fatty acids. Typically, the first double bond in almost any naturally occurring fatty acid, which I'm going to switch my color and I'm going to highlight this, is going to occur at carbon number 9. So here we see number 9. Now, what's also noted on here is that your carboxylic acid is carbon number 1. And that goes back to your organic priority numbering or your organic carbon priority, or sorry, atomic priority. So that is significant. Now, in polyunsaturated fatty acids, this right here brings back some organic terminology that you may or may not have forgotten or remembered. They are not conjugated. Now, the way that I always like to think about the positioning of double bonds in a polyunsaturated fatty acid is I like to look at it as I have a pattern of a double bond, followed by a single bond, followed by another single bond, followed by a double bond. So in my mind, whenever I think of polyunsaturated fatty acids, I think DSSD. So double, single, single, double, single, single, double. Okay, so that's the way that my mind processes these different fatty acids. Now, okay, let me go back for just a second. Does anyone have any questions about any of this right here? Okay, cool. So when we look at those saturated fatty acids and polyunsaturated fatty acids and the monounsaturated fatty acids, that C18 colon 1, that numbering scheme, 18 colon 2, well, there are basically two major um, nomenclature strategies, schemes, whatever you want to call it, for labeling fatty acids. For instance, here we've got stearic acid. This is C18 colon 0. Now, that tells us we've got 18 carbons and 0 double bonds. So this is a saturated fatty acid. Next up is right here. I'm going to switch color. I'm going to go with like a magenta. This is 18 colon 1. So we have one double bond. Now, we have a delta numbering scheme that delta is going to indicate exactly where that double bond is. And our numbering for the delta scheme starts at carbon number 1, our highest priority carbon, and just adds up from there. Now, with that in mind, what numbers, if we're doing the delta numbering scheme for linoleic acid, it will be 18 colon 2. And then what numbers would we define or would we put for to follow our delta in linoleic acid? Morgan, yes, absolutely. Morgan, your streak remains alive of like contributing and, you know, knocking it out of the park. Great job. Thank you very much. I think like almost every single class, you're like this, and yeah, awesome. Great job. Thank you. So this would be 9 and 12. And so we note that 18 colon 2, delta 9, and delta 12. Now, when we get to another polyunsaturated fatty acid, alpha linolenic acid. Okay, well, again, with this delta numbering scheme, it's delta 9, 12, and 15. Now, one thing that's a little bit funky that you probably are noticing here is that we have this or, N. Man, I've never heard of N fatty acids. Okay, so is everyone good with the delta numbering scheme? To me, it's kind of like straightforward. Okay, great. Now, we're going to do this, and then we're going to look at a quick top hat question. Our omega numbering scheme, we're starting from our highest numbered carbon. So this is also known as N fatty acids. Actually, you know what? Just because we're kind of crunched for time, I'm going to go to the top hat question, and I'm going to work through this one, and then we'll revisit omega numbering. But I want you to kind of simmer on this. So I'm going to add some more time just so I can talk through this one. So you're looking at a fatty acid that is that's 18 carbons long. You're trying to name this fatty acid with the omega numbering scheme. What carbon number should you start with or start at for this specific numbering scheme? Okay. Omega, if you think about the Greek alphabet, omega is the last character in the Greek alphabet. So in this case, what we're going to do is our highest numbered carbon. Well, our fatty acid is 18 carbons long. So we can either start with carbon number one, which is what we do for the delta numbering scheme. So I'm going to add in here delta, or you could start at number 18, which is for the omega, because of the fact that, well, N equals number of highest number carbon N number. Morgan, absolutely. You're absolutely right. That's exactly what you're going to do. And so we're gonna we're gonna work on what Morgan just added to the chat, and we're gonna develop that a little bit more for our omega numbering. But in terms of numbering or working backwards, you're starting at the with the omega numbering scheme, you're starting at the highest numbered carbon, and then you're going to work backwards. And so Morgan added N equals the highest numbered carbon and the number being subtracted until the nearest double bond. You're absolutely right. So an omega-3 fatty acid, for example, you're starting at 18, and then you're going minus one, two, three. Okay, so it's the third carbon from the end. Okay, I hope everyone was able to add to, I added 15 more seconds. Go ahead and make a contribution to the top hat question. Thank you guys for coming to class. Great job, everyone. I hope that you have a great, what is it, Wednesday? And I will see you again on Friday morning. I'm going to stop my recording, stop the share. Great job, everyone. Thank you. And look up Mr. Barbieri. It's exciting. It's interesting.